Welcome. Today I'm going to go over section 2.4 on continuity. And most of what we're going to talk about is continuity at a point. So continuity at a point is going to give us what we need to extend it to continuity on intervals, which is what we're going to use going forward with calculus. A conceptual or intuitive idea of what continuity means, a curve drawn without lifting the pencil is continuous. That's not the mathematical definition, but that concept of pencil is continuous. Okay, I'll try to work around this glare spot I've got. Okay, so what we're really going to investigate to get a handle on continuity at a point is a break in the graph. A point where you, if you were drawing it, you would have to lift the pencil and put it down again. A break in the graph is a discontinuity, or a point of discontinuity. We're looking at a point of continuity, but really it's better to start with the kind of the opposite. Let's look at the different types of continuity. Excuse me. Look at the different types of discontinuity. So first, I want to do these with graphs and also talking about the symbol for the function. But the first one, we'll look at this x value a and a real simple function here, almost a linear function, but it's not a line, it's a line with a hole in it. And in this case, f of a is undefined, and it's called a hole. So this is a type of discontinuity. One that's really closely related to it is almost the same thing, really. You have a function with this hole in it, but it's actually, the function's defined for that value. It's just not where it would need to be to make the graph without lifting the pencil. So it's also discontinuous. In this case, the limit, we do have a limit in this case from the right and left, and it's where that hole is. The limit as x goes to a of f of x and the actual value of the function are not equal. So that's another type of discontinuity. And both of these, the hole, and I call this a hole also. Like there's a thing for it, but it's still a hole. These are both removable discontinuities. So both examples of a removable discontinuity. So in other words, you could fill this in and have a continuous function. You could move that point and have a continuous function. As they are, though, discontinuous of the point A. The next one we'll look at there's actually different varieties of this, but I picked this one because I think it covers the basis. So again, simple function, two lines this time, but also they're not connected. This is a situation where the limit, and this would be the x value a, the limit as x goes to a of f of x doesn't exist. And so this is a discontinuity. In this case, f of a is this lower one, the solid dot. It is defined at a, just not up there. And then to the right, it's this other function. This one's called a jump discontinuity. You're probably already tired of writing the word continuity and discontinuity. You can abbreviate it. But a jump discontinuity, not a removable discontinuity. I would have to change this whole shape up here to make these two into a continuous piece and still be a function. So there's one other type of discontinuity. We're going to look at it a little bit more later, but it's really different from these other ones in that the graph looks very different. It's got different features, and that's the infinite discontinuity. You are familiar with it because we've seen asymptotes before. In fact, let's do two infinite discontinuities because there's some variety. So this first one, I've got an asymptote where my graph is going to go up on one side. The limit from the left is infinity. And it's going to go down on the other side. The limit from the right is negative infinity. This one, I want to do something similar, except my limit from the left is infinity and my limit from the right is also infinity. So, this limit at this value a, plain old doesn't exist. It goes to positive infinity from this way, it goes from negative infinity from this way. They don't line up. For this one, they do line up. This one, the limit is infinity. This one, the limit is infinity. They're equal, but they're not equal to a real number. The function isn't defined at x equals a. And more importantly, you can see there's two separate pieces that don't connect. So these are both discontinuous functions. Discontinuous at a. Discontinuous at that point. The rest of it, though, we're going to see a result about that a little bit later. These pieces are continuous. Even in these previous functions, these pieces are continuous. The function as a whole isn't. So that's pretty much the variety of discontinuity that we're going to see. Let's go ahead and look at the definition of continuity. And it's this, f of x is continuous at, let me say, at x equals a, or continuous at a, for short. And that's really what I'm defining. We're still talking about continuity at a point, so the function is continuous at the point a if the following three conditions hold. The first is f of a is defined. That really means for our graphs, we can't have a hole there, an empty dot, or an asymptote. It's either got to be a part of the curve or a solid dot. F of a is defined. The second thing, the limit as x goes to a of f of x exists. And I'm pretty sure they mean exists as a real number, but if it exists and it's not a real number, this third condition will exclude it anyway. One more thing about this. This means that the two-sided limit exists. So the left side, the left-hand limit and the right-hand limit have to both exist and agree and be equal. That's another mouthful. I'm going to leave that off. But the third thing is the really significant condition, and it really makes these two look like, oh, well, if you got this, of course, it is like that. The third condition is that the limit as x goes to a of f of x equal f of a. So this limit, of course it has to exist, but it also has to equal the defined value of a. And that's what it means for f of x to be continuous at the x value of a. So these next couple questions are, is the function continuous? And the answer is no, but what's a better way of saying it is, where is this function discontinuous? Or which x values make this function discontinuous? And so we're going to use those conditions really to see that these two functions aren't continuous. The first one, f of x equals x squared minus 4 over x minus 2. So for this one, we've worked with a function like this, if not this exact function before. If x is equal to 2, we have trouble. So that's the a that we're talking about. If it's not equal to 2, this isn't a very exciting function at all. If this is, if x is not equal to 2, then this function is equal to x plus 2x minus 2 over x minus 2, which means it's just equal to x plus 2. So let me say that again. For any value of x that isn't 2, this function is just equal to x plus 2. It's just a line. In fact, I'm going to graph it, x plus 2. It's got a slope of 1. And here's the problem right here. So the line goes up that way, and the line keeps going that way. It's fine. But right here is the x value of 2 that I can't use in my function. It's not in the domain. The rest of the function just looks like the line y equals x plus 2. And with this graph, and knowing that we can't use the number 2, we can see that this function is, f is discontinuous. Discontinuous at x equals 2. I guess that's part of an answer to this. The other thing is, what kind of discontinuity is it? So it's a rational function. If I just looked at that, I might think there's an asymptote. There isn't an asymptote. It's just a removable discontinuity. Or you can just call that a hole. So this is locating it at x equals 2, and this is classifying it. Let's do another one like this. Look at the discontinuity and classify it. So for this one, I'm going to have a piecewise defined function, negative x squared plus 4, if x is less than or equal to 3, and 4x minus 8, if x is greater than 3. So piecewise function, it's a function that's defined by two separate formulas depending on which part of the domain you're in. And that's actually a good place to start, looking at the 1, 2, 3 is the cutoff. So less than or equal to 3, or to the left of 3, I'm going to use this function. To the right of 3, greater than 3, I'm going to use this function. This one is a quadratic function. And it's actually a pretty nice one as far as quadratic functions go. If you look at negative x squared, that's just a parabola that opens downward with its vertex at the origin. Plus 4 would shift it up 4 units. So the vertex is actually right there. Now, To get an idea of where this function's going to go, remember it is a downward opening parabola. This part's not that complicated. This part, it's going to come down, but it's not going to be, it is going to be defined at 3, but it's not going to be defined by this curve to the right of 3, when x is greater than 3. And for that part, we're going to look at this one, which is a linear function. But first, where does it go at 3? And if I check this one, x equals 3, it's negative 3 squared plus 4, negative 9 plus 4, negative 5. It's going to be 1, 2. Here, and I'm putting it as a solid dot because the or equal part, that's where the function's actually defined for x equals 3. And this part, downward opening parabola. It stops there, but it doesn't stop on this side. So this one just keeps going to the left and down. Now to the right, we're going to use this, to the right of 3, we're going to use this other function. I really just need to know where to start. And if I were to put in that 3, remember 3 is, for x equals 3, we're using this other function. But if I was to use 3, what I'm looking at is the limit from the right of this function. And I'm going to put an open dot there. But 4 times 3 minus 8 is 4. And from there, the function, it's a linear function. Slope is 4. Intercept is negative 8. If I traced it all the way this way, it'd be negative 8. But we're going to the right of 3. And it's a slope of 4, so it's very steep. I made a mess of my function, but it goes up to the right. And from this picture, you can see, first of all, this function's continuous everywhere except f is discontinuous at x equals 3. So continuous everywhere else, but discontinuous at x equals 3. And it is a jump discontinuity. So we've located it and classified it. So as I mentioned earlier about the polynomial rational functions, there's a classification for those that we can use what we already know about the domains of rational functions. It's a theorem in the book that polynomial and rational functions are continuous on their domains. And remember, a polynomial all real numbers are negative infinity. A polynomial domain is anything. A rational function domain is, how can we say this? All real numbers except where the denominator is 0. I think that's really the easiest way to say it. If you don't know what the rational function is, if you do, you look at the bottom polynomial, find its zeros, and those are the excluded values. Everything else is not only defined, but continuous. Here's a really simple example. F of x equals 3x to the 4th minus 4x squared is continuous for all x in R. I don't know how much we've used this so far, but the double back R is shorthand for real numbers. In this case, we're looking at a polynomial continuous on its entire domain, and its domain is the whole real numbers, so it's continuous on the whole real numbers. A second example, though, g of x. G of x equals x plus 1 over x minus 5 is a rational function. So it's continuous on its whole domain, but its domain isn't the whole real number line. We can't have x equal to 5, otherwise we'd have the 0 in the denominator. So this one is continuous on the whole real number line except the number 5, which is negative infinity to 5 and 5 to positive infinity, excluding the number 5. All right, there's one other concept that is kind of a refinement of the definitions we've already had. It's actually an extension of the idea of continuity, but we've looked at one-sided limits and two-sided limits, and this is really where that connects to continuity. This is called, well, let me write the first one as a sentence, and I'll just shorthand the second one. So function f is continuous from the right if the limit be a little bit more careful about this. A function f is continuous from the right at x equals a if the limit as x goes to a from the right of f of x is equal to f of a. So that's almost the same as the definition of continuity, except that we're talking about a one-sided limit, in this case from the right. So the limit of the function as x approaches a is equal to the function value at a. Again, though, for this definition, just from the right-hand side, from the positive side. The other one is f is continuous from the left at a if the limit as x goes to a from the left is of f of x is equal to the function value. So it's possible that one of these but not the other can be satisfied. And we actually saw that with our jump example. I'm just going to kind of sketch in the relevant part. Remember, this was the, we had a number before. I'm just going to call it a because we're talking about a here. But for this x value of a, as I come in from the left, the function has a limiting value that's equal to the function value. So, and as I come from the right, it has a limit, but it's not equal to the function value. The function value is down here. So this would, if this is my function f of x, is continuous at a from the left. In symbols, that's the limit as x goes to a from the left of f of x equals f of a. Now that's the same thing right here. So that's the last concept in the section, but I have an example of it's like one of the later homework problems And I know these are a little bit challenging because you're supposed to build your own function with very little direction. But they have enough direction for you to get the picture of the limit or the whatever kind of discontinuity they're drawing here. So this is number 158. And it says, sketch a graph such that these four things, the domain of the function is the interval from 0 to 5. The limit as x goes to 1 from the positive side, from the right, of f of x, and the limit as x goes to 1 from the left of f of x exist and are equal. So the limit exists and they're equal. It doesn't say that the function's defined there, but it doesn't say it's not. The third thing is f is left continuous at 2 but not continuous. So it's left continuous but not continuous, so I guess it's not right continuous. But and f is right continuous at 3 but not continuous at 3. And then finally, there's another condition here. Removable discontinuity at x equals 1. Jump discontinuity at x equals 2. And a couple limits here. The limit as x goes to 3 from the left of f of x is negative infinity, and the limit as x goes to 3 from the right of f of x is 2. Wow, that's a lot of conditions. I hope I can still fit the graph on here. The good news is this first one, we're looking at a really narrow section, so I'm going to make a graph where I'm just going to go 1, 2, 3, 4, 5. If it seems like I need a different scale on the other axis, maybe I'll do that, but that's 5. That's where this whole business is living, according to the x-axis. Now at 1, it says that these exist and are equal. The limit is the limit as x goes to 1 from the left, and the limit as x goes to 1 from the right exist and are the same. But nowhere else, right here it says something about 1, but nowhere else does it say what a value should be. So I'm on my own for that. I'm just going to say 1. I'm not putting the value there, but I'm setting up so I can put my limits. That it's going to be coming into 1 from the left and coming in to 1 from the right. I don't want to get anything on 2 yet. But yeah, it could be up here or down here. It doesn't matter. I think this will work with the rest of it because I see there's an f of x value of 2. Maybe not. Let's look at the next one. F is left continuous at 2. So we were talking about 2, but not continuous at 2. So maybe it's right here coming into that point at 2 from the left, and then a jump so that it's not continuous at 2. For 3, I'm starting to wish I made my axes wider. but I think it'll work. Right continuous at 3, but not continuous at 3. So whatever it is at 3, it's going to be coming into that value from the right, but not from the left. And here's where we get that information. That limit from the right as x goes to 3 is 2. So at 3, it's 2. And my function's coming into that value from the right. At 5, I guess we just put it something at 5 and something here too. It's nothing specified about 5 or 0 here. Now the only one I really, I think we really took care of this. The removable discontinuity at x equals 1, it's 5. We don't even need to put a point. The jump discontinuity at x equals 2, that's great. It's a jump. But for x equals 3 from the left, now this is the one we have to look at. As x goes to 3 from the negative side from the left, that needs to go to negative infinity. So what I'm going to do is, at 3, even though I've got a value there, so by the way, this isn't a rational function. It's got a value defined on its asymptote. Rational functions don't have that, but it's okay. From the right, as we approach 3, it's got to go down to negative infinity, the asymptote thing, coming at that asymptote from the left-hand side. All right, and this is relevant to, I think it's number 157 and 161 are the ones like this where you're given some conditions and you have to make a graph. It'll have you exploring each of these different concepts that they've introduced. Let me put the homework list up on Moodle, and hope to see y'all on Tuesday.